Professor. Uh, my name is Hardy. Um, in this figure, we can see three different kinds of absor absor abs abs absorption absorption spectrums in a picture. And the first is hydrogen. Second is sound sound. The third is sodium. And they the they choose 400 to 700 nanometers part of spectrum to compare. And we can see the F dark line and the C dark line of sun's spectrum is the same with hydrogen spectrum. This line and this line, yeah. And D line sun's spectrum is the same with sodium. This and this dark line are produced by the absorption 是这样的 yeah, of certain frequencies of light by the elements contains in the gas surrounding the star and is surrounding the suns, and these elements produce the light, and this signal can the dark line can represent specific elements, like we can see the hydrogen have this line and the sodium have this line, and they represent these two elements. Yeah, and we can, yeah, we can know hydrogen and sodium are part of elements in sun's atmosphere. In this figure, we can see four spectrums with. I looked the book. It said it is galaxy, and yeah, four different distance galaxy. This one is very far. This one is nearby the Earth. Yeah, and they have the four. This four spectrum is their spectrum, and we can see it have the almost same spectrums. Distribution of the dark lines. You can see the first is the too thick dark line. Yeah, and after they very similar, and the dark line between dark line, the distance and the dark line's intensity is almost the same. And the astronomers found this phenomenon, and they found that the distance from the Earth more increase, and the overall spectrum shifts toward to the red, and the more distance farther away from the Earth, and the greater the extent of this shift. They called it red shift, and this concept is like the Doppler shift. Yeah, and the astronomers observe this. Observe the atomic spectrum, and it indicates that the whole galaxy is moving away from the Earth after the Big Bang. Our universe is grow up, yeah, bigger and bigger, and the distance is increase between the star. Yeah, I am finished. It's the conclusion. Conclusion is the universe is grow up.
Okay, so first, Tiffany, why does redshift tell us that the star or the galaxies are moving away from us instead of approaching us, coming to us? Why? 为什么红移是这些天体是离我们远去，而不是离我们越来越近？
就是发出的那个可见光的波长比较长，所以要怎么讲？
因为可见光的波长比较长，所以它就是离我们远去。Because it's in the long wavelength part of the visible light, so the stars are moving away from us. That's what you said. Victor, do you have something to add?
我想法也差不多，就是它远离的时候波长就会比较长，然后靠近的时候，因为波长就被挤压，然后就比较短，就是两个相对，然后就是波长就比较短。对。
Victor said, because the objects are moving away from us, so their wavelength will become longer than they usually than they would be if they are not moving. Okay, that's what I understand you. All right, so the argument is more thorough compared to Tiffany's, because Tiffany's argument is a little bit fragmented. 你讲的有点碎片化。Okay, so yes, that's the case. Okay, and then Steve, can you go to page 1? Can you explain this word, halo? What is halo?
好，让我想一下哦，就指的是那个光环。
光环
是。
太阳的光环。
应该是指的是那个太阳外部那个结构，应该是日冕层还是什么东西的吧？
Okay, that means the outermost part of the stars. Okay, because stars are all made of gas, right? Stars are not like planets, which have solid substance, like your table. Stars are all made of gas. However, when they mention halo, it means actually the most external part, all right? The most external part of a star. And then this is important because that means, you need to now read this sentence clearly. It means these dark lines are produced by the absorption of certain frequencies of light by the element containing halo of gas surrounding the star. That means they are actually produced by the element at the most external part of a star, not the internal part of the star. So that's why I want you to pay attention to this term, halo. It's the most external part. Because in next week, we will talk about element formation. Then we will talk about element formation in stars. Then you will know stars have shelled structure. Okay, it's not like all stars are homogeneous. They have shelled structure. So you need to pay attention whether we are talking about the internal part of a star or the external part, the most external part of a star.
我可能觉得我这句话写错了，就最后一句话。
Why not? That's good. We can know hydrogen and sodium are part of elements in the sun's atmosphere, which is very good. Okay? Although I don't know if you understand when you wrote the sentence. Okay? That means hydrogen and sodium are present in the external part of the sun, but probably not the internal part of the sun. Okay? Okay, good. Thank you. Hardy.
Okay, hello everyone. My name is Gary. Okay, you can see this figure. The x-axis is distance of galaxy, and the y-axis is retreat velocity of galaxy. So you can see the figure shows that the farther a galaxy is from Earth, the faster it's moving away. So it can prove that the universe is expanding. Okay, you can imagine a situation that there are 3 people and start from the same place at the same time, and one is walking, and one is running, and one is riding a bike. So the man who is riding a bike, is faster than the runner, and the runner also faster than the walker. So the distance between them will be farther and farther. So okay. So you can put this concept into the universe. So when the Big Bang occurs, the galaxy B is faster. You can see this picture. Okay. The galaxy B is faster when the Big Bang occurred. So it will move faster, right? So its distance will be farther from Earth, from us. And then the galaxy A is slower, so it will move slower. So it will be closer to us. So the speed is constant, so they will farther and farther. It will be farther and farther. Okay, finally, the scientists discover the relationship between the distance and the speed of galaxies. And then they came up with the expression of the universe and the Big Bang. Okay.
Chloe, and do you know how the scientists just get those data? I mean the retreat velocity of galaxy.
I think it's the Doppler effect.
Do you know how they measure the distance of galaxy? Alan.
I think they get the distance of galaxy from the Hubble's law and Big Bang theory, because when they compare the distance of galaxy and retreat velocity of galaxy, they find it to be the positive.
Gary, do you agree?
你可以再说一次吗？我刚刚在想。
I think the distance, they find the distance of galaxy from the Hubble's law and Big Bang theory, because when we compare the distance of galaxy with the retreat velocity of galaxy, they find it to be positive.
Axel, do you agree what Alan said?
I don't agree, because I think that to prove the and the Hubble law, you have to get real data about the distance of the galaxies. Like if you cannot say, okay, so I think that's the relation. So I think that the distance is that. I'm not sure how they found the distance of the galaxies. Maybe it's by comparing the intensity of the emission of their lights, or maybe by doing trigonometry to find the distance. But I don't think that you would first found the Big Bang theory and the Hubble's law, and then you found the distance, because it means that you found your theory on something, some data you don't have.
Okay, very good. I think it's a very nice discussion, so I appreciate both of your comments. I think Alan said because of the Hubble's law, so they can figure out what the distance is. And what Axel said is we need to first have the distance of galaxy in order to acquire the Hubble's law, right? So which one is cause and which one is effect? 因果关系是什么? So in this figure, this is cause. 这是因 ，OK， and this is effect， 这是果。So therefore, it's very important for you to figure out what is the cause and what is effect, and how do you know which one is cause and which one is effect. You need to know which one is independent variable. 哪一个是独立变数 Okay, you need to know which one is independent. And indeed, this one is an independent variable. I want to ask in this class, does anyone know? Actually, Axel just said, how do you know the distance of galaxy? You do it by triangulation, 三角测量, or the emission of light, 测光. We will talk more about this in this lecture. You acquire this information by this real measurement. Okay, so usually when you do real measurement, your data is usually independent variable. Okay, and apparently if you get a relationship like this and you say this is the Hubble's law, then Hubble's law is actually dependent on this and this. So this relationship is not independent. And I want to ask, again, maybe we have more B student. Henry, what does the slope tell you?
You mean the trend of this slope? Okay, I think because basically these dots, they show us when the distance of galaxy gets longer, and so the retreat velocity of galaxy also gets faster. So,
right, that's already Gary already mentioned that. But actually, from the slope, you can acquire a very important number. Do you know what that number is?
Maybe it's like the origin, like we can see that it's passing by the 0. So it means when you have 0 velocity, you are 0 centimeters away from our galaxy.
So you mean
So
the
it's a
origin of
linear-
the universe?
Yes, the origin of the universe. But I don't know because it's distance of the galaxy, but is it from us or from the origin of the universe?
No, it's from us.
So I think that it's just telling us that it's a linear progression, and when you have no retreat velocity, you have no distance. So everything is emanating from the same space, from the same place, and it's like a proof for the Big Bang theory.
Right, that's indeed a very good elaboration of the figure. However, it still doesn't tell me which important number can we get. Does anyone in this classroom want to answer this question? Which number? A very, very important number can be acquired. You want to raise your hand? Okay, can you please pass to her.
Hubble's constant.
Hubble's constant? Not really. Maybe that can be acquired from this figure, but that's not the most important number we want to know.
The farthest distance from us that we can see, like the commonly seen universe. I don't know.
No,
No?
it's not the number I want to know. It's actually written in the textbook. Anyone want to tell me? How about you? I guess you probably have heard of it, but you don't know that it's actually from this figure. No? You can know the age of the universe. We will talk about this more later in our lecture. Okay, thank you, Gary. So thank you for staying with us in this lecture. And I can see that you have, I actually really appreciate your assignment. I can see that you really do the assignment yourself. So I appreciate all the effort of ever opening your reading material and look for the answers. So I hope that this kind of practice will be helpful for you. Okay, so we want to talk about the Big Bang today. So before the break, we will just talk about some historical review of this question. So apparently this kind of topic came from some natural questions about the universe, like how big is the universe, how old is the universe, and was there a beginning? This kind of very natural question, which probably will never have an answer. However, the Big Bang theory provides solid scientific answers to all these questions. Here, I italicize solid, not because of my own opinion, but actually it's written in your reading material. So the authors thinks it's actually a very solid theory for the questions here. So why is that? So to begin our adventure, we need to ask, or not we, but previous scientists, they ask, why is nighttime sky dark? So you might think, oh, what? Isn't that natural to have dark nighttime sky? So here is a number. 2019 star count estimates that there was 1 × 10⁻⁴ of stars in the observable universe. Which means if you look at the sky and if your vision is so sharp, you can actually identify this number of stars. But of course, our vision is not that good. So usually if you look at the sky and there are a lot of stars, all you see is just a messy background, all right? However, here is the so-called dark sky paradox. Okay, it's actually brought up by these scientists back in the 19th century. So this is you, the observer, and this is the universe of stars. We know there are 10⁻⁴ stars in the sky, so there are a lot of stars. So in theory, the night sky that you should see is like this. Okay, full of stars. You should never see a dark background because there are so many stars like this, which is, of course, not true. We see every day dark sky, right? So why is that? Okay, so that's the so-called dark sky paradox. So here are some explanations. So the first explanation is, explanation 1, the universe is finite. Finite in Chinese, it means 有限的. Okay, so you can think there is a boundary of the universe. And here is us, the earth. Okay, so, and therefore, at the most external part of the universe, at the boundary, the background is black. And then you see this. But however, of course, I think this doesn't really explain the dark sky paradox, because in theory, you should see this, okay? The second possibility is the universe is infinite, 无限的. There's no real boundary, but there is dark matter intercepting the most distant stars. So these are dark matters, like this. So these are possible explanations. However, there are problems with these explanations. Of course, for the explanation 1, I think if there is a real boundary for the universe, you should see a nighttime sky full of stars. Furthermore, physics tell us these stars, if the universe is finite, they will ultimately collapse. They will collapse, okay, if the universe is finite. For the explanation 2, if there are really dark matter intercepting the stars, then we should be able to see glows from stars like this. This star will emit sunlight and it will shine on the dark matter, so you will see the glow, like what you see the night sky above cities. You will see a glow of light from the light of the city, okay? So that's a problem for these explanations. So therefore, as early as the first half of the 20th century, there was a scientist proposed a conjecture. Conjecture means guess, 猜想, okay? That means he doesn't have any proof. It's just a guess. Conjecture for the paradox. That is, it's a cosmic egg. Okay, 宇宙蛋, cosmic egg. Okay, like this. So the universe is expanding, like this. But it's a conjecture. Okay, so then today we will talk about the Big Bang theory, which actually nicely explains the dark sky paradox. Then there are actually several lines of the evidence. The first one is redshift, which is your assignment. The second is the distance of stars, which is not very well discussed in your assignment, so we will talk more about this. And lastly is the cosmic microwave background, but this is a little bit too complicated, so I will not talk about this. Anyone who is interested in this topic can read the textbook. So it's written in the textbook. So the first part is the redshift. So you know that redshift, we can say, stem from spectroscopy, 光谱学 in Chinese, spectroscopy. Is actually a physical approach to study the chemistry of celestial objects. So therefore, in the future, when people ask you what are the ways to study the chemistry of stars, it's actually all by spectroscopy, okay? All by spectroscopy. It's very rare. Actually, so far, it's impossible to obtain any physical material from stars because stars are so hot. It's impossible to land on stars. It's possible to land on planets, but not stars. So to study stars, we need to rely on spectroscopy. That usually means telescope, 大型的望远镜, okay? And then to do this, you need to have a basic understanding, or you need to refresh yourself. Light as electromagnetic phenomena. So these are the whole spectra of electromagnetic waves that we know of. And as we know, visible light is just a very small part of the electromagnetic waves, right? So here is the basic equation. I think you all remember. It's a frequency, F, is the light, I think C is the light speed. Lambda is wavelength. So now there's an inverse relationship between frequency and lambda. So longer wavelengths have lower frequency, and the other way around. So, and you also need to pay attention that for, of course, in the visible light, in this direction we have shorter wavelength, and in this direction we have longer wavelength. And this is high energy wave, low energy wave. And visible light, the red light is here, violet is here, okay? And then you also need to know X-ray is here and radio waves are here. And actually in next, or maybe in 2 weeks, we will talk about telescope using the principle of radio waves. Okay, so you see that these are all used to study celestial objects. All right, but you already know they are dark lines in the spectrum of the sun. What are they? All right, so here I would like to remind you atomic assumption. It calls the so-called Frauen, it's German, I think, Fraunhofer spectrum. It means this. So this kind of spectrum has a name. It's called Fraunhofer spectrum. So that means the incoming light is, you can think of it as a photon. So we know that light has a dual property. It can be wave or it can be particle. So the light, you can think of it as a photon, and this photon can actually interact with the electron. So this electron interact with the incoming photon, and it will absorb the photon. And this will cause the dark band you see in the Fraunhofer spectrum. Okay, so this is absorption. However, actually after a while, because the electron, you know, this is ground state, 基态, 基本的基, and this is excited state, 激发态, okay? 也是另外一个基态, okay? Excited state. And at the excited state, the electron is not stable. So after a while, it will emit the energy that is absorbed from the photon. And then this will create emission. Okay, so this is an absorption emission cycle. And actually, because in your class, there are no students joining the lab of Professor Kuotong Jian. So in his lab, there is an instrument called AA. AA is the abbreviation of atomic absorption spectroscopy. 原子吸收光谱仪. And the principle of this 原子吸收光谱仪 AA is actually based on this. All right, so these are the atomic absorption of photon is a reason that caused the Fraunhofer spectrum. All right, so I think these sentences are the sentences from the textbook. So I will not read through it because I think Hardy did a good job, so I will skip this part. And what about the other stars? Because the spectrum here is the sun. And then for other stars or other galaxies, that you actually also see these spectrum. However, while these spectrum, they tend to have the same pattern, like a thick, thin, 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 thick, etc. These spectrum tend to locate at different part of the visible light. And they tend to move towards the red end of the visible light spectrum, right? So that's the so-called redshift. You all know Doppler effect. You are third-year students. Any of you interested in physical oceanography? Does any of you know that there's a very important instrument in oceanography which make use of the Doppler effect?
ADCP.
Very good. And do you know what's the A mean?
I don't know.
You don't know. Hang on. Acoustic Doppler current profiler. Okay? This instrument makes use of the Doppler effect. However, by the first term, acoustic, it means based on sound. Okay? So you know that it's not like what we are talking about today, because today we look at light, right? Light has a different speed compared to sound, and ADCP actually make use of sound. Why can ADCP monitor the current speed? Why? Because in the current, there are always particles, right? There are always particles. And the particles tend to move together with currents, right? And if a ADCP is standing here, and the current is moving like this, then it will know by the principle here, which we will talk about later, it can, by having its, it will always emit a signal upward, and then by detecting the time difference, it will be able to know the movement speed of the particle, which is usually the speed of the current. So that's the principle of ADCP. And I think ADCP is a very great invention, 很伟大的发明, because you are not a generation, and I am not a generation without ADCP. So in our generation, we live in a world with ADCP. And the good thing of ADCP is you have an instrument sitting here, and it can detect the current for maybe the whole water column. 它可以测整个水层的流速哦, while you only need one instrument here. However, this is not the case in the world or in the generation without ADCP. In the generation without ADCP, you need to, if you want a current profile, which means you want current data for many different depths, if you want 10 depths, then you need to buy 10 current meter. And then you need to attach the current meter at 10 depths. And that's very complicated, time-consuming, and expensive. So I think that's the reason I think ADCP is a very great invention for oceanographers. All right, so Doppler effect. How do we acquire number from Doppler effect? Because we know ADCP use this principle, and it can acquire speed, which is a number, right? So this is based on the speed, or in this case, this is based on the speed of sound. We know this is the speed of sound, right? And if this car is not moving, it has 0 speed, then this is you, the observer. If in this case we say, we will hear 100 beeps per minute, okay? This is a presumed number, 一个假设的数字, okay? So this is what you will hear, 100 beeps per minute. And now, if the car is approaching the observer at a speed of this, you can see that this speed is a tenth of the sound speed, right? Then, as the observer, you will hear this, 110 beeps per minute. In other words, if you hear 110 beeps per minute, you can actually back calculate the speed of the car. And then, if it's leaving you, you will hear 90 beeps per minute. So that's a principle. But it is a very simplified version, of course. That's all you know. If an object is approaching the observer, the frequency of waves emitted by the object will be higher. How will you explain? You already explained. What does the extent of shift tell you? It tells you that they are leaving us at different speed, okay? Then, can you quantify the velocity? Can you? Of course you can, as long as you know what? The speed of light, right? Then, in theory, you can. But of course, the calculation is probably not as simple as I showed in previous slide. But in principle, you know the light speed, then you should be able to know the retreat speed. Now we focus on the distance of stars, because this part appears to be not that well discussed in your assignments. So how do we determine celestial distance? There are actually several methods. We will talk about geometry, standard candles, and there is a third method, but this method I will not talk about it too much. We will focus on the first two methods. The first one, the geometric approach, has a special name called triangulation. Okay, so I am a geography undergraduate. So previously, 我以前是地理系的. Okay, and I remember very clearly the first assignment I got as a geography freshman is to map the so-called 最月湖 of NTU using triangulation. Okay, at that time, that was back in 1998. There was no Google Map. There is no smartphone. So all you have to do is So the TA told us that you need to walk through the lake, and then you need to calculate the baseline using your footstep. Okay? And then you need to measure some object, maybe a rock, in the middle of the lake using your vision, like 15 degree, like this. And then using this approach, you can basically map the lake, okay, without any like a Google map or whatever. That was our first assignment. So I have a very strong impression of triangulation, right? And it's a very time-consuming process. Okay, so that is, you need to know the distance and you need to know the angle. Then you will know the distance here. So that's the purpose, the distance from here to here. That's what you can do on Earth, but how can you do this for the space? You need a baseline, right? And then the first baseline we use is this. So this is the orbit of the Earth around the Sun. The first baseline we use is the so-called this astronomical unit. Astronomical unit means 1 AU means the radius of the orbit. Okay? And then the actual baseline we use for the so-called annual parallax is 2 AU. Here, 1 AU, 2 AU. We use 2 AU. Therefore, in theory, that's what an astronomer should do when he wants to make annual parallax. When the Earth is here, maybe in spring, he needs to measure once the star, measure the angle. And then later, half a year later, in autumn, maybe, he needs to measure the same star again, the angle. Okay? Then, with this information and with this astronomical unit, he will be able to calculate the distance from the Sun to this. Okay. What's the limitation? Of course, you can imagine that here we have a lot of number, but in theory, to make a long story short, for example, now I'm looking at Hardy, okay, with a pen here. If my measurement is not that precise, like this, okay, from here to here, then the distance between me and Hardy is probably maybe 1 light year already. 就是你只要差一点点，你的那个距离就是差1光年。Okay? Because this baseline is relatively short compared to the distance here. So a small change in the angle will result in a very large difference in distance. So you need to be able to measure the angle very, very precisely. However, there's always a limit. Okay? So that's the limitation. I won't read the detail here. So you only need to know astronomers need to measure the angle very, very precisely. Therefore, annual parallax is basically only applied for maybe in the solar system or maybe some other celestial object around the solar system, but not more. Okay, it has very, very limited applicability. So now we talk about another way to do parallax. I will explain annual parallax in Chinese 就是年视差，就是一年做2次，okay. Then there is another parallax called secular parallax. In Chinese, I think it's called 好像是什么，有点像是长年视差，就是很多年期的。Okay, so how does that work? This is the Milky Way. Okay, the Milky Way. And we know the sun is here. The sun or the solar system is actually also rotating. But of course, we don't feel it. Okay, and it's rotating around the galactic core. Okay, it's rotating So how do we make use of this fact? It's very easy. Like if I'm the astronomer, I will measure my angle to another galaxy when I'm 30 years old, okay? And then maybe when I'm 80 years old, I will do this again. Then we have two angles, right? Then the sun is maybe from here to here. Then we have two angles. Don't laugh. You think this is very small, but this baseline is much larger than 2AU, than the annual parallax. And then maybe my daughter, when she is 30 years old, she can measure the same star again. And her daughter, maybe again. Then you can extend the baseline longer and longer, and your measurement will get more precise over time. That's how it works. Okay? I hope it's clear. With this approach, scientists have already measured the distance of all the stars within the Milky Way with this approach. Okay? So you know that within the Milky Way, the distance was obtained by parallax or triangulation. This one is more difficult to understand. Standard candles. I try to make it easier for you to understand. To do these standard candles, we need to use a very specific kind of stars. It's called variable stars. In Chinese, we call it 变星. 变就是变化的变, 变星. Its definition is a star whose brightness as seen from the Earth fluctuate. So its brightness fluctuate. So sometimes it's lighter and sometimes it's darker, like this. However, there are different kinds of variable stars. It's not that every kind of variable stars can be used for standard candles. We need a specific kind of variable stars. What we need is so-called Cepheid variable stars. In Chinese, we call it 造父变星. Cepheid variable stars. Okay? So I don't know if it works well, but I think in principle, the brightness of this star should change on the screen. It's not that clear. Okay. Cepheid variable stars is a member of a class of very luminous variable stars. Very luminous means they are very bright. Okay, very bright. Very bright variable stars. And most importantly, it has periodic pulsation. So this is its change of brightness over time. It will get brighter. So it's a little bit like tides. 就有点像潮汐. Brighter, darker, brighter, darker, and it's periodic. 规律的. Periodic. Okay, so these kind of variable stars, they are named after Delta Cephei, the first star of this type identified. So now to give you a better impression of what this is all about, we will talk a little bit about constellation. So this is the Cepheus. So in Chinese, I think 仙王座, Cepheus, okay? And here you see a woman. Her name is Cassiopeia. 仙后座, okay? And then you see a young woman here, Andromeda. 仙女座吧. So they are a family. Father, mother, daughter, okay? Then Cetus 是什么呢? 金鱼座. Although I don't think it's look like a, well, it has a tail here, maybe. Cetus is a whale, okay? And the most famous one is Perseus, 英仙座, so you must know this. Medusa, right? So he has the head of Medusa in his hand. And then, of course, we should not forget Pegasus, 飞马座. Okay? So you probably know the story that I'm going to show you. And Delta Cephei is at the left shoulder of Cepheus and is a very famous variable star. So this is Cepheus, and that's his queen, forgot the name, Cassiopeia, and daughter Andromeda. So the thing is, Cassiopeia is a beautiful but arrogant woman, according to the story, and she thinks she and her daughter are the most beautiful woman in the universe, and this irritates Poseidon. So Poseidon is 海神. So this irritates Poseidon because Poseidon thinks his daughter is more beautiful than these two women. Okay, so the angry Poseidon sent Satyrs, which doesn't really look like a whale. I think it's Godzilla. Okay, so he sent Poseidon to destroy the city where the family, this royal family lives. And then Pegasus, he bring Medusa to petrify the satyrs. Okay, so you know there's a movie back in 2010, Clash of the Titans. Nice movie, so I would recommend this movie to you. We are talking about standard candles. So standard candles have to be classical Cepheid variables, okay? And this type of stars, they were discovered by female astronomers. So she discovered that brighter Cepheid variables in the Magellanic Clouds, 麦哲伦星云. So Magellanic Clouds are the closest galaxy from us, appear to have longer periods. So this is the periods of the Cepheid variables, and this is the luminosity, how bright the star is. And then she made an assumption. She assumed that all Cepheid variables in the Magellanic Clouds are at the same distance from the Earth. This assumption is generally correct because overall the Magellanic Clouds are very distant from us. Okay, so it's a little bit like if we talk about the distance from Taipei 101 or the Taipei, the presidential hall. We would say, okay, they are of the same distance from us. 就是说，假设我们今天在讲台北101或者是台北的总统府，对我们而言，这两个对我们现在的距离是差不多的。So she made the same assumption. In the Magellanic Clouds, there are different Cepheid variables, but she assumed that they are all at the same distance from Earth. And then here we need to talk about this relationship, which always annoys me. I think sometimes it's difficult to explain this. So this is a light source. It has an intrinsic luminosity, which is how bright it is, okay? And then you, as the observer, you cannot watch the light source as close as it is, right? You must observe it from a distance. Then you can only observe its apparent brightness, okay? And then apparent brightness is B, intrinsic luminosity is L, and this relationship tells you that the longer distance you are from the light source, the lower the brightness you will observe is related to distance. However, as I said, she assumed that all the Cepheid variables, they are at the same distance from Earth. So in this case, this one was set constant by her. Therefore, in principle, we could only observe brightness of stars. But here she said this is equal or comparable to luminosity. Okay, so she discovered that brighter variables in the Magellanic Clouds appear to have longer periods. And then the periods is the blinking rate of the variable star, and the luminosity came from the apparent brightness of the star. And then the good thing is periodicity is easy to measure. Luminosity is not. That's the good thing. Okay. Now in Chinese again. 他发现，这种变星，它的周期越长，它就越亮；周期越长就越亮。那为什么这件事情是好事呢？而且有一个关系在，原因是因为你后来就会发现，其实周期性，就是说它的那个明暗的频率，会比你要去测量一颗星有多亮还容易。好，就是为什么这是一个好事。好，对于我们测量是一个好事。Okay, so this is the so-called period luminosity relationship. How to make use of this relationship to measure distance? How? So far, there's nothing related to distance. Okay? So in the Milky Way, where we are, we also have Cepheid variables, right? And I already tell you, in the Milky Way, the distance of all stars can be measured by secular parallax. Okay, they are already measured by an independent method. So we know distance, right? And then we also can measure their apparent brightness. And because we know the distance, in principle, we can also calculate its luminosity, right? And then because in the Milky Way, we have 800 Cepheid variables with different periodicity. We can classify them. We can maybe select a group of Cepheid variable with the same periodicity, and then usually they observe a relationship, like the longer the distance, the lower the brightness. Okay, then this is actually, you can think of this as a calibration curve. Calibration curve. And then, if now we have another Cepheid star in another galaxy with the same periodicity, like maybe we say 10 days. Maybe they all have 10 days periodicity, okay, these stars and this star. Then, this star, we can use, okay, sorry, I choose this one. We can use the relationship because here we have the distance brightness relationship. We can use this relationship to calculate the distance of this Cepheid variable star. And then we can assume that this Cepheid variable star, its distance is representative of the galaxy where it is. How? In Chinese. 在银河系，我们也有变星，好，我们有800多颗造父变星，好，造父型变星，好，这些800多颗呢，我们每一颗都知道它的距离，为什么？因为我们是用那个视差，好，前面都已经讲过了，好，那我们就把它分组，好，就说，这一颗的周期是10天，那一颗是15天，这几颗是20天，好，然后你就会发现，他们基本上可以得到这样一个关系，就是假设距离越近，好，就是在这边 y 越小，它的亮度就会越大；距离越远，它亮度就会越小。所以你就可以得到一个关系式，好，就是亮度跟距离之间的关系。好，那前提是你这一个里面它们的那个周期都要是一样的，比如说都是15天。好，那今天呢，我们现在有一个亮度跟距离的关系了，好，它就是有点像一个校正曲线。是用我们自己银河系的去校正的，好，然后呢，你就去看这一颗呢是另外一个星系的，好，比如说什么麦哲伦星云啊，或者其他星云，哈，那在这个其他星云里面，其他的星星我们都管不了了，好，因为它们太难理解了。但是假设它是一颗造父变星，那我们 照复型变星，我们就可以利用我们在银河系得到的这一个关系式去外推出它的距离。然后我们外推出它的距离之后呢，我们就假设这一颗照复型变星它所代表的，它所有的距离就是可以足以代表它所在的那整个星系。所以为什么到后来我们就不会去说单独星系了，我们就会单独星系里面的某颗星，我们就会说整个星系它的距离是怎样，因为星系的距离基本上是用照复型变星去算出来的。Question.
The fact that the Cepheid of same periodicity have the same brightness, is it just found by empirical means? Like we just have observed it and we have deduced it. We have nothing more than.
Do you mean is there a physical reason for this?
Not the physical reason, but the only proof that we have is just like empirical, like we observed it.
Mm-hmm.
No, it was just a quick question, or if we had another, proof. I don't know how to formulate.
I think so far these are all empirical.
Okay.
These are empirical. I'm not sure because I'm not an astronomer if there is a reason for this.
Okay.
But I think there should be some reason for this, probably related to supernova or something.
Okay.
All right, so that's how we figure out the distance of different galaxies. That's the reason we say this Cepheid of that galaxy, it is the lighthouse or standard candle of that galaxy. All right? When we come back to this figure, which is your assignment, we now know that this is from redshift, and this is from, if it's within the Milky Way, we use parallax, 视差. If it is beyond the Milky Way, we use standard candle. That's how we do it. At the end of our discussion, I ask, what is the significance of this relationship? And you can say a lot. However, I think you all answer this well. However, that's what I want you to answer. Which number? All right? So we know velocity, by definition, is distance divided by time, right? Therefore, if you recast this equation, you will acquire time is distance divided by velocity, right? And this is distance. And this is velocity. Okay? Therefore, that's the reason the scientists can calculate by looking at the slope and with some calculation, very simple calculation, they reach the conclusion that the universe started 30.7 billion years ago. That's how they acquire the conclusion, using this simple equation. Okay, and then they also reach the conclusion that there must be a beginning. And the universe is still expanding, so the so-called Big Bang. However, with this graph, I would like to come back to Axel's comment because you said there should be an origin, right? However, this is a figure from the textbook. The textbook tells you, because right now what we see is the stars are moving away from us, right? So here in the textbook, the authors draw a similar, here, this is a train station, and there are two trains leaving at the same time away from the station. And this is the observer. When the observer is sitting here, he will find out that, okay, this train is leaving and that train, the second train, is also leaving. However, if the train starts from here, he will reach the same conclusion. If the train starts from here, he will also reach the same conclusion. So the author said, it's impossible to know what is the exact coordinates where the universe start. We can only know that the universe expanding, but we don't know where the exact origin is. Okay, conclusion. The velocity of galaxies was determined from redshift. The distance was determined by parallax and standard candles. And there's a third method which I skipped. And then based on the Big Bang theory and the Hubble's law, we know that the age of the universe is 13.7 billion years ago. 130亿年前. Okay, a very exact number. Question?
Can I ask that will the Big Bang stop? Will the Big Bang stop expanding?
Stop?
Yes.
As far as we know, I don't think it will stop. Because the redshift is still observable. So at least from your life, it will not stop. And for my life, it will not stop. Okay, but if you read the textbook, it will tell you that, it tells you that actually the expansion rate has changed. I don't remember it's changing faster or slower, but it will not stop in our life. So I want to again encourage you, because I think from what I see today, I think you did a good job. So I hope that you are not that afraid of English. Yeah, and I think what I have seen today, you can, like what Gary and Hardy did, you can write some complete sentences. And then when you need to give the presentation, it doesn't even matter that you read just the sentences. Okay, at least it's a good practice for you. So for A student, please explain. Herzsprung. I'm not sure if it's German. Russell diagram. Okay, in Chinese, it's called 赫罗图. Okay, 赫罗图. You can next week you can call it HR diagram. That would be easier. HR diagram. And this is not in the textbook. However, I think this is so important for you to understand the life of stars. So I decided that this should be included as an assignment. And there are a lot of internet material. And in this time, if your similarity is higher than 50%, it's okay. Because I asked you to look for internet material. So you need to look for HR diagram. Then in the HR diagram, you will see the x-axis is surface temperature. The y-axis is luminosity. So you need to explain, what does surface temperature mean? What does luminosity mean? And then here we have these. It's called main sequence. So what does main sequence mean? And you can see in this version, they draw stars with different size. Why? How do they know the size of the star? Can astronomers really see that? So how do they know the size? And then please explain the life history of a sun-like star on the HR diagram. So where would the sun go? Does it travel like this, or this? That's for A. For B, explain this figure, chart of nuclides. So this is from the textbook, the chart of nuclides. So first, you need to explain the following terms: isotopes and isobars, stable isotopes and radioactive isotopes. Then, what is band of stability in this figure? What is that? Then, how to read alpha decay and beta decay in this chart. How to read electron capture in this chart. And then, what is the relationship between neutron and proton in this chart? Neutron and proton. You can find answers in the textbook.